Welcome, everyone. Today's speaker is Professor Khmaladze. He is a retired professor at the School of Mathematics and Statistics at Victoria University of Wellington, New Zealand. He received his PhD in 1972 and the Doctor of Sciences habilitation in 1989. In 1991, he was granted the title of Professor of Probability Theory and Mathematical Statistics. From 1991 to 1997, which were quite difficult years of post-Soviet Georgia, he served as the head of the Department of Probability Theory and Statistics at Khmaladze Mathematical Institute. During this time, the department received the highest number of international grants within the Georgian Academy of Sciences. He later held positions at the University of New South Wales, Sydney, from 1996 to 2002, and Victoria University of Wellington in New Zealand from 2002 to 2022. He is a fellow of the Royal Society of Academy of New Zealand and the Institute of Mathematical Statistics, IMS, publishes leading professional journals like the Annals of Statistics, the Annals of Probability, and 4 other annals. He's also a foreign member of the National Georgian Academy of Sciences. His research contributions include works in distribution-free theory of statistical testing, empirical processes, and innovation theory, in set-valued analysis in statistical problems, and in statistical theory of diversity. In 2016, Statistical Science featured him in their Conversation series. Today, Khmaladze is a chair of the board of the Asia-Pacific Seminar in Probability Theory and Statistics. It's Probability and Statistics, which is the major professional seminar in that region. We are very honored to welcome you, Professor Khmaladze, for your talk, and we look forward to your talk on what probability theory and mathematical statistics do.
Thank you very much. Thank you very much for letting me come here and speak to you. I heard about Stellenbosch before, and then I never thought that I would be here. And now here I am. I'm very happy, very honored. Thank you for coming. This extra subtitle in speaker's restricted experience, at one hand, it's not very good because you speak only on some small things. But you will probably agree that probability theories are huge. For example, I will not be speaking about percolation theory, which is a very big thing. On the other hand, it is good because it is what I'm responsible for. So I can answer all questions because this I understand very well. So I'm speaking about things which I relatively well understand and therefore can be kept accountable for what I say. The idea of this public lecture pushed me into thinking in general terms about what we are doing and who we are. You see? You always are technically involved in your research. You are doing this, trying to prove things and discover this and so on. But sometimes you should zoom out and look, what is this that we are doing? And then I should say that we are people who belong to this big army of other humans who are trying to understand and to investigate. Maybe I should add not only to understand and investigate, but to tell others. If you understand something and you tell others, then you are a good researcher. We do this research as research should be done. We try to do it like this. So you remove this bit, this bit, and you come to naked truth, very truth of things. So you come to something which is quintessential to the phenomena which you investigate. If you don't do this, then the research is incomplete. We are trying to do this. In mid-60s, there appeared a very influential book of Michel Loeb called Probability Theory. A huge book with very large content of absolutely abstract measure theory, many different integrals, and so on and so on. But in the introduction, Michel Loeb was saying that at the end of his introduction, he was saying, besides in mathematics, as in any other form of poetry, the reader has to be a poet and possessed. So that is, he connects directly in his mind and tells us that mathematics is also a poetry. That is not because of florid expressions and beautiful phrases and so on. Absolutely not because of this, but because the essence of poetry is to say in few clean, absolutely exact words, the feeling or the situation which you want to say. And this Gwendolyn Brooks, I discovered myself quite late, only some 20 years ago. American, Afro-American poetess, much celebrated. And these are just 6 lines. Not that I should read it to you, you can read it yourselves, but it's 6 lines. And you read it and you see the whole generation here in front of you. You understand the generation, you commiserate with them, you almost live with them. You see everything in 6 lines. So this made impression on me when I looked on what she has done. One other example which stays with me all my life is the example of Antoine de Saint-Exupéry. And he was a pilot. He was fighting pilot during the Second World War, but he was also the author. And if you know the book, this Little Prince, it's a very famous book. It's just novel. And he was the author of this, and de Gaulle then said that I knew Saint-Exupéry and so on. Exupéry, we don't know how he died because he disappeared. But one thing he said was this, that airplane, the best airplane is not the one to which you cannot add anything more. The best plane is the one from which you cannot subtract anything else. So this absolutely clean machine for flying and fighting. And then it is very good. And I think this is very good. So we are trying to do this. When we are lucky, we achieve this. If we are not, we achieve it to a less degree. Now, we are trying to understand what? We are now trying to understand random phenomena. Random, right? Just listen to this word, random. That's chaotic. That's not deterministic. That's not one which you can determine by something. Out of the blue, something happens and we say we understand this. Yes. We try to understand this and we there discuss and derive and prove the laws which are as strict and as unavoidable as any other law. For example, law of gravity. Law of gravity you observe, you measure, and then you have this law. Okay? You know, 2 bodies attract each other in this and this way. But in this world of complete randomness and unpredictability, we discover things which are absolutely strict laws and cannot be different. I will give you an example, but first let me start with this first model of random phenomena. You have this coin and you toss the coin. You observe heads and tails and you count the number of heads in that many tosses. And then you divide one by another, look on relative frequency of heads, and then it fluctuates, and then we believe, talk so much about this, and now everybody believes that it converges to half. But my fingers don't know probability, and your fingers don't know probability. We are simply tossing coins. And so this is something happening in physical world. What I will do here, I will not look on experiment. I will completely ignore experiment. I will turn to the whiteboard and will multiply some distributions, then go to Fourier transform, then go to some limit, then go to inverse Fourier transforms. And finally, I will obtain mathematical statement, which tells me that frequency, relative frequency, must converge to half. And this completely ignoring experiment. I am not copying, I am not modeling experiment. I am proving my things with the exact mathematical rules. But then when I see what is happening and what I proved, then I see that they match each other so very nicely. To some extent, it is maybe a miracle. Why my fingers behave in such a way? They don't know that I will come to the whiteboard and prove something. But they behave in such a way that this result agrees with what I will prove. When Blaise Pascal was doing this experiment for himself, it was not obvious for him that Well, you should be very clever to understand that it's not obvious that physical law exists. But he was sitting and tossing this coin and counting because he wanted to convince himself that in physical world this is happening. And it was time when the law of large numbers didn't exist. And what I can do now, Blaise Pascal couldn't do in the 17th century. This is if you think a little bit, it is in a very strong contrast with what is happening in physics, for example. In physics, our colleagues will design and conduct ingenious experiments, very difficult, very beautiful, very interesting experiments to measure things like gravitational waves, right? And then they imitate and model whatever they see in their measurements, in their mathematical expressions. And as I told you, I'm not doing this. Not that we will not see an experiment later on, but probability theory is mathematical discipline. And I derive it not by imitating something, while physics do this. They measure, then they say, what I measure is this. After so much talking about poetry and philosophy and this and that, I come to absolutely prosaic example, absolutely practical. It is something which belongs to what we call now data science. Absolutely prosaic. But I want to show that even here there is a room for clean understanding what's happening. So this is a price. How can I? Yep. In New South Wales, the electricity market is deregulated, so it's free. I produce and sell, and you buy and you pay me, and that's it, how it is. And this is a sequence of 3 years of daily average prices. Price changes every half an hour, then you derive daily average, and then you plot the sequence of these prices. And this is 3 years of such data. Now, what is this? This is a histogram. This is the first thing any statistician. Where is it? Yeah, here. Any statistician will do. So the prices in this interval from here to here are that many. The days when the daily average price was between this and this are that many. And the days where the average price was, daily average price was in this interval are that many, and so on. So this is a histogram. Absolutely raw thing without much fantasy. I produce histogram. Everybody does. You look at this, and I have seen papers and people who are talking about this and saying, well, this is probably truncated gamma distribution of this and that and so on. So it is tempting to start talking about what this is straight away without analysis of what is the nature of things which you observe. But if you look on this is much nicer histogram, right? And this histogram is derived from this. So behind this histogram is that. And this is almost Gaussian. But this was observed by understanding that some prices are sums of independent random variables and therefore should be Gaussian. And some prices should be different distributed because of this and this, and so on and so on. There is some good statistical analysis behind coming to this. But it is sitting already here. Okay. So I want to say that the raw analysis is very naive analysis and rarely brings to real understanding of phenomena. Now, I apologize to those of my kind listeners who know this probably better than I do. But this is Rutherford's model of radioactive disintegration. This is such a beautiful example, and I couldn't resist temptation to tell you a little bit about it. So a mission which happens on the sun every second, right, which warms up, and a mission which was happening in physical laboratory around the world in many places. How it was happening in the beginning of 20th century, it was a huge question. And then what Rutherford said was this: then there is a nucleus, and from this nucleus alpha particle is emitted. but there is nothing preparing here, ripening and making it more and more ready, and then emission. No. No, there is nothing, no preparation. Emission is just out of the blue, absolutely spontaneous. Why should it be spontaneous? Is it not more natural to assume that something is happening in the nucleus, some inner processes? But he said, no, nothing is happening. Well, then he assumed B. He had trouble with persuading himself that B is correct. And B is this, and the particle is emitted, and it flies within this material, radioactive material, and why does it not excite? Can it excite or inhibit, maybe, emission from other nuclei? And he had some doubts about this because he saw very short intervals between one emission and another emission. So he was thinking maybe this emission provokes that next emission, and that's why I see such a short intervals. But eventually he said, oh, suppose not. Suppose one emission does not make any influence on any other emission. Therefore, the C is just a very simple assumption. We don't have to discuss it. But is it not that I said that phenomenon of radioactive disintegration is absolutely spontaneous, absolutely chaotic, absolutely unpredictable? And yet, if you derive the density of these random intervals, you will obtain this expression. And this is not a chaos at all. This is one specific and not very complicated expression of density. Many of you probably know that this is exponential density of probability distribution. And this follows from A and B. So chaos somehow disappeared. There is no chaos anymore. Here it is. It can't be anything else. If I look on the random variable, capital N, which counts the number of emissions in interval 0t, well, from U, 0t. And here I count how many emissions did I register on my Gale counter. Then this is N. It's random. Well, does it have probability distribution? Yes. Can it be 0? Yes. Can it be 5? Yes. 21? Yes. What are the probabilities? Well, probabilities must follow this very specific distribution. This is so-called Poisson distribution. And if A and B are correct, this distribution cannot be anything else, although there is a sea of all possible distributions. No, it must be this, which is written here. So this is example of law, which is unavoidable and must be followed, and which I derive using A and B, not ever seeing any emission anywhere. Oh, this is a strange example, but I thought maybe I'd tell you. Imagine 1812. And the Napoleonic Wars in Europe, after he invaded Spain, Germany, Holland, and everybody was happy then with French armies. They were behaving more or less decently. And then he decided, and why he decided, it's difficult to say, he decided to invade Russia. And he went into Russia, and he went all these many thousand miles, not encountering any resistance. And he came in the winter of 1812 to Moscow. There was only one battle during this campaign, and he won this battle. And then he entered to Moscow unopposed. And he was in Moscow, but then it was very, very cold, and his supplies failed. And he was there with 500,000 people with him, and the houses were burning, and he only had on his mind how to feed these people, what to do with these people, and how to finish this quasi-successful campaign. And then there was a courier from the capital, from Paris, coming to this freezing Moscow, and bringing with him the 2 volumes of Laplace. Not because Laplace was a great scientist for Napoleon, probably he was, but because Laplace was finance minister of Napoleon. And he was influenced on what would be sent to Napoleon and whatnot. And he sent his 2 volumes. So this is analytic theory of probability. And in there was the following regards. You see, he was discussing the following thing. He already knew this, what we call now Gaussian or normal density of this shape. He also knew that if one random variable has behavior like this, and you have some of those, then they will also have normal density. The density also will be like this. And if it is average, it also will be like this, only narrower. And he has had this concept of variance, what we now typically denote by sigma square. He already had these quantities. He can use it. Good. And he did. And he said, if I take average, then the average of, if one observation has variance sigma squared, then average will have sigma squared divided by n. That is much smaller. Then he used it in a way which nowadays every laboratory person is using this. But he was the first who realized to do this, and he had tools to do this. And he applied it in a great man as he was, in the following way. He said, well, astronomers observe the movement of moon around Earth, and then you should follow the celestial mechanics equation, right? But astronomers notice that, for example, at some day of the month, the moon is slightly off. But within each observation, which was difficult and so on, within each observation, this little bit off was within accuracy of experiment. But he combined many results together and looked on average. And average has this accuracy much higher because the variance now was sigma squared divided by n. And therefore, he says, well, it is certain for me that the moon is systematically deviating from the prescribed trajectory. And there is a reason for this, he said. The reason is that Earth is not sphere, but geoid. So I don't know, Napoleon was reading this in Moscow or not, but imagine this in freezing city. And well, we understand that Newton worked on this and other people worked on this. We understand that in Arctic circles, they conducted many experiments on this and so on. But the statistical reasoning, then I can take average, and it's also Gaussian, and it has much smaller variance, was his achievement in this book. That's Laplace. In principle, evolution of, well, formation of probability theory as mathematical discipline started late. These are great names which usually are associated with this. And I can speak about correspondence between Huygens and Pascal and Fermat and so on. But you see, this is mostly 17th century. Just imagine ancient geometry in Egypt, how much younger this is, how much more late this is. Probability theory. Imagine arithmetics, such an old mathematical discipline. Even imagine algebra, which in medieval times was a very good part of already mathematics. And this started much later. It started later, it took some time, it took several centuries, 2 or 3 centuries. And the final step was achieved in 1931 in a small book in German by Kolmogorov. Kolmogorov spent his young ages in Germany under Hilbert, and that's why it was German, what he wrote. The statement that probability theory is one of measures, is measure. Measure is class of functions which you use in probability. Area is a measure, volume is a measure, weight is a measure, potential is a measure, charge is a measure. So give me some set and I will give you the volume of it. Or give me it on a plane, I will give you area of this. And this function, area as a function of the set which I gave you, it's called measure. And then they say, well, probability is also a measure. And already since bias at least, we had the concept of conditional probability of event A given event B. If B happens, what can I say about probability of A? And this is extremely important question. But we needed notion of conditional probability of A given B when probability of B is 0. That is, we needed the statement of what is the probability of A under condition which will never happen. It looks a little bit strange, but it's not very strange if you remember what is a massive set is formed by conditions which will never happen, which have probability 0. It was absolutely crucial for formal mathematical development of probability theory, and Kolmogorov realized that the work of Radon and Nikodym, which is a work in measure theory, is relevant. And he defined this conditional probability in a specific way. And after that, we became mathematics. Let's go back to this tossing coin and taking averages. I said that, well, I toss the coin, and suppose I believe that without my proving anything on the whiteboard, then the frequency will go to half. So that is, I believe that averages will tell me the truth. Averages will bring me to the truth if I only do experimentation long enough. And now I want to show you that it's extremely dangerous. And basically, it is incorrect. And I know this is incorrect because of mathematical work. And no person with common sense and with just usual reasonable understanding of things would be able to come to this, but it's nevertheless true. It is true even with binomial trials. You have 100 trials and you observe how many heads do you have. Suppose you get this relative frequency and they say, well, probability is almost this relative frequency. It's extremely dangerous state. In a little bit delicate questions, it will be very wrong state, because we should take into account that the frequency or relative frequency is very much random, and we should understand the nature of this randomness. But here's an example which is maybe more striking and more interesting. Maybe you heard about martingales. No, it doesn't matter if you didn't, but martingales is the class of very important stochastic processes, very, very random. They fluctuate wildly, and they go like this. Now I look only on positive martingales, and then what I say is this. What the fact is the following. So these positive martingales converge. They do converge. So they stabilize to something, but they converge to random value. That is, in one laboratory, they measure something and they see that the result of their measurements stabilizes to some quantity, and they declare this and they publish a paper, and the paper is very successful. And then there is another laboratory measure the same thing, and they measure and then see what is happening in their measurements, and it converges. So it converges to here. And they also publish a paper, and they are also successful, and there is a big discussion between them who is right. Both are right. Because they should have known this mathematical fact that positive martingale converges to random value. And now I will show you this. If it works. Yes, I think it will. So this is how it is generated, but it doesn't matter. This is my positive martingale. And change it a little bit. Yeah. And it starts with 0.5. And then it evolves. This is number of observations. And I stopped at 200 observations. Now, with any hitting this button, they will generate new trajectory of exactly the same process. The same probabilistic characteristic. Everything's the same. But see, does it not converge? Yes. It fluctuates a little bit. Maybe not a little bit. It fluctuates here a lot. And then changes a lot at least, and then it converges to something like 0.9. And what happens now? It converges. But it converges to something which is 0.5. It again converges. Now we have seen this, but now it converges to 0.2. You see, there are different trajectories. Each trajectory converges, but the limit is random. Therefore, averages are not telling me the truth. Or I should understand that the truth which they are telling me is this, that the limiting distribution the limiting random variable is a random variable and not deterministic limit. And I should study this and understand. Okay. Let me close it. Don't save it. Now, this is something which starts with main idea, which sounds probably just outward silly. It's not possible to ask this a priori, you see yourself. So we will agree that biological objects, they age. Biological objects during their life accumulate damages and accumulate the force of mortality or failure rate increases, and at the end, the chances of failing is higher than at the beginning. So this is property of all things, many things. Biological objects all are like this. Even bridges are like this. They accumulate damages. But now I want to look on the duration of a reign of Chinese emperors. Duration of reign. But reign also should accumulate damages, right? It should be famine or lost war or this or that. You don't go and shoot prime minister just out of the blue. There should be some discontent in public, in the country, in people. They should dislike this person. He should accumulate damages. But now the whole idea that we go and see what is the behavior of statistical ensemble of duration of rules of Chinese emperors. And they have recorded history for 23 centuries. Not 23 centuries of empire, but of recorded history of this empire. Extremely strange and long and stable phenomena. And then, is it really sensible? And now I'm trying to say that yes, surprisingly yes, because similar thing happened in analysis of text. So Divina Commedia, one of the greatest poems of humans, right? Great medieval poem in Italy by Dante, everybody knows. And then I go there, I look on this poem and I say, well, what will happen if I start studying Divina Commedia as if Dante was throwing his words at random? No, this is just impossible question. You must be a person with void of any intellect to start doing such thing or assuming such thing. It's not possible. It's like a naive statistician walking around with his histograms and touching great things. But if you do this to Divina Commedia, then you will end up with the discovery. So it is not silly. It leads to discovery, which probably later I will tell you about. So therefore, maybe if it leads us to something, this analysis of Chinese emperors, it will be interesting. But if it doesn't, then I will look as a fool to you, and that's it. But I hope to show you that no, there is a little bit of discovery. What happens is that we will see that this huge statistical ensemble of duration of reigns is no different in its behavior than emission of radioactive particles. So that the speed of emission or rate of emission does not change during these 23 centuries. Technology changes, laws changes, production of food changes, everything changes, but the statistical ensemble statistical nature of these rules does not change. Behavior or rules, or duration of rules, behavior is the same as emission between particles. With half time, physicists are always using this quantity as a half time, half lifetime isotopes. So half life for Chinese emperors is 10 years. We have some explanation for this. We try to explain this, but first we want to justify that this is true, and it was big work because I will show you only one graph, but there are many graphs and very rough analysis because you can't come out with this statement just based on one statistical test. It's not possible. It's not good. Look, this is duration of lifetimes. And you see that around age of 85, 89, the probability of failure, death, increases sharply. Right? There is nothing like exponential curve which should be like this. Absolutely not. This is absolutely not exponential. And this is what we understand because, well, the humans accumulate damages, and therefore, towards the end, the probability of death is high. But now let's have a look on duration of rules of Chinese emperors. So this solid black line is data. So it's based on data. It gives us frequency of different durations. And this dotted line is exponential approximation. Imagine 23 centuries of data, and who cares about your statistics and your exponential distribution? They live and they rule. And they care about the empire. And as a result, it is such an exponential thing. And this is 10, very much in the middle. 10 is very much quantile of half. So midlife of a rule is 10 years to 23 centuries. One more thing is very, very strange here, because let me divide the group of emperors into two groups. Those who became emperor young and those who became emperor old. And those who became young, is it not true, just normal human logic, that, well, they have long life in front of them, and therefore they will rule for longer. And those who were old and became emperor, they would rule for shorter times. This is not true. So this is data on distribution of rule length of young emperors, and this solid line is old emperors. And you can tell me, well, there is a difference. No, there is no difference. Statistically, it's very, very well agrees with the statement that probabilistic mechanism behind both things is the same. They are not different. So the age of emperor at ascent plays no role. And here are the British monarchs. And, well, starting from Henry. And this is duration, or empirical distribution of duration of rules of young monarchs, and this is of old monarchs. And now this is a difference. And compare now this difference with this difference. Well, those of you who observed Poisson process or heard about Poisson process or like Poisson process, they may appreciate the nature of this. So this is, we started from minus 231 when the first record was made. And then we follow, and they will count here at 5 plus 500. It's chronological moment, 5 centuries, Anno Domini. And then we count how many rules we have seen before that, and how many rules before this, and how many rules like this. And therefore, this line counts the number of rules from the initial moment to this moment, current moment in time. And then this is a mean estimated midline. So this is such an excellent trajectory of time homogeneous Poisson process. So this is Poisson process, this huge empire and emperors who lived according to Poisson process. Simple explanation is this. There is explanation. We cannot come with a better, but we believe that this may be reasonable, and some people will agree with us. So imagine that there is a pressure in all of us. We live under pressure. And the pressure is some stationary process applied to all of us, and we somehow cope or not cope with these pressures. But sometimes the pressure is a stationary process. And sometimes the pressure will be very high. But this is emperor. If usual pressures will destroy us and affect our lives, it will not affect emperor. But if suddenly pressure becomes high, then it will kill emperor. And therefore, the number of the stoppage or duration of life, duration of rule of emperor from one emperor to another is a distance between two high level crossings of the pressure. But if underlying process is stationary, then these times are exponential. This is mathematical fact. And therefore, it explains why duration of rule is exponential. Because only very high pressure can upset Ampere's rule. But then it will upset in unpredictable way. I don't know, somebody can help me in keeping the time? Yes, okay, yeah. Yeah. 10 minutes? Don't I have 1 hour? I will start bargaining with you now, you see. Okay, then I skip this. Okay, I'm sorry. This is a scatter plot of age of ascent of Roman empires. We started not with Chinese empires, but with Roman emperors. And when we saw this empirical distribution already resembling exponential, and this smooth line is exponential distribution function, we thought that we as statisticians, we discovered statistical evidence of decline and fall of Roman Empire. So yes, of course, if the top rule, the top power in empire is so unstable, of course it's decline and fall. But let's go to China, which is very stable and exists for such a long period of time. And we will find counterexample. And we went there and found this phenomenon even in more clear. Okay. This average I will show you. Imagine that this arrow at the end of this is actually the source of light. It emits a beam of light. And suppose the observer does not see this, but he's standing here in my hand drawing, sorry for this. He is standing behind the screen, and what he sees in these dots where the spot of light appears on the screen. This observer can see. No observer certainly will look on his screen as X and will put somewhere 0. And what he wants is to decide where this thing is, the source of light. But it can rotate. It freely rotates. It has no preference for any angle with the same chances. It rotates freely, and sometimes in this direction, sometimes in there, sometimes in this direction. But the observer says, well, I will observe these spots. I will stay here patiently long enough. I will take average, and then I will know where this point is, because the average of this will come close to this point. Okay? And I will discover where is this source of light. And he stays and observes and observes and observes and observes and observes and gains nothing. Because what is happening, well, here is some couple of formulas. I wrote this in case there is a question, so that I will explain why what I will say now is true. But I will say that distribution of one observation, any one, first, 27, one observation, without any average, has the same spread as distribution of average of them. So average does not produce increase of accuracy at all. So therefore, by observing and taking averages, the observer will not gain anything at all. See? So therefore, it is good to know some mathematics in probability theory, because then you will not fool yourself and not say, well, I will take average and I will be all right. You will not be, not always will be. Say it again. I have how much time? 5 minutes? Oh. Thank you. Because I wanted to show you this, so that you will see it with your own eye and do not believe me. So this number is average of 1,000 observations. Average of 1,000. And this is just the first observation. And I generate this axis, generate these spots, position of spot on the screen. And this is average, and this is one observation. And so far, looks like average is closer to 0, where it should be if some things are correctly said. Well, let's see. Well, 1 again. Yeah. This is a good example for me. This is one observation, 8 to 10 to minus 3, and this is average, 3.6. And if you look at this long enough, you will realize that average fluctuates no less than one observation. So then this is true, mathematically it's true. Well, some other examples of this sort we can demonstrate. No, don't say. But I wanted to show you some other things, so introduce some other field of statistical research here. And this is the theory of large number of rare events, or statistical theory of diversity. We know that when you observe and ask how many different species, then you have so many. How many different sites, how many sites are on the internet, and so that we will visit them. Oh, enormous amount. How many different words? Oh, a huge number of different. Yeah. And this is theory of diversity. Now, how do I analyze such things? How can I discover there, with these small frequencies, how can I discover the law? It is not true anymore, it's not useful anymore than to take frequency and divide by number of observations, because this will be extremely small number and probability is small. And what is good in saying that small frequency corresponds to small probability? There is no information in this statement. Yet we can analyze this. Let's see how we do this. We say that we have n different events, which is a huge number. We conduct n trials, which is also a huge number. Both are very large numbers. And then I observe what I observe. This is mu I is frequency of i's event in n trials. And then mu nk is a number of those events which I see exactly k times in my sample. For example, number of those events which I see only once. Number of species which in my very long sequence of observations I saw only once. Number of species which I suspect are there, but I saw them not. Their frequency is 0. This is mu and 0. So these are quantities which we operate with. And then the mathematical definition is this. It was created somewhere in the end of 80s. So if the number of unique species, unique words, unique items, divided by total numbers, different items which I see in my sample, if this fraction does not vanish, it converges to a positive limit, then I will say that I have a large number of events. How this can happen? Because if I have some box in which only one ball fell, and I continue throwing balls, that's continued observations, then one more ball will hit in this. And then from being unique, it's being unique. Now I have 2 of those. Yes, but there will be new one, which will be unique. And therefore, number of unique events will not disappear. If it will not disappear, then it is large number of events. But then the mathematical fact is this. And for any k, this fraction has a limit. From this follows that for any k. And Zipf's law, such as celebrated law, you see, in physics, you can see hundreds of papers on Zipf's law. Georg Zipf was American, only of German origin. And this CK is such a beautiful form. It is first difference of this harmonic series. 1 over k minus 1 over k plus 1 gives you this. That's Zipf's law. And if we look back, go back to Divina Commedia, then it has 100 songs or 100 chapters. And each chapter is extremely symmetric work. And each chapter contains is 1,000 word words long, almost, well, very close to 1,000. Therefore, the total size of Divina Commedia is 100,000 usages of words, the size of Divina Commedia. Well, out of these words, 14,000 are different words, which a normal person would say, well, it's approximately 8 times, each word was used 8 times. 8 times this is 100,000. And it's absolutely wrong state. Absolutely wrong. Well, because half of these words, which are used, have been used only once. 6,500 were used only once. They are rare words. If you drop these words as unimportant, you will drop huge variety in color and beauty of the language. They're extremely important. Well, number of words which Dante used only twice is also large. It is this. So this is indeed 1/6 of total number of 13,000. But when 2 is 2, this is 1/6. And if you continue, you will find that the Divina Commedia agrees with the Zipf's law very, very much. Now, it's unthinkable that Dante was sitting and counting something, just absolutely silly. But something in him, some feeling of beauty, a correct composition, of good structure, somehow induced him to write in the way he wrote. And then suddenly it became a Zipf's law. And this I like so very much. I very much hope that you may agree with me. So this is fragmentation. This is another source of a large number of the events. The fragmentation process. They are fragmenting. These are they are splitting the stones. But you just imagine Neanderthals 500,000 years ago. And they were doing this. 500,000 years ago, Cro-Magnons were already Erectuses, no, not Erectuses, Sapienses. They were hitting and splitting the stones to make all sorts of tools. The only difference here is this mallet. Oh, well, clothes, because Cro-Magnons didn't have any cloth. But also this mallet, because this has metallic head, but they didn't have metal at all. And this sort of activity, after thousands of years, is still with us. We are still doing this here. Well, you can say, no. This is modern fragmentation and splitting stones, but this is not very interesting. This we know very well. But this, because of hugely old nature of this activity. What else do we have from that time? Maybe barbecue. They were frying meat and we are frying. Otherwise, such an old activity, fragmentation. We will not fragment stones, but we will fragment probabilities. So, suppose I ask you Q binary questions, and I ask you all to fill the question. 10 questions later on, this will be example, but in general, Q. Each xi is your reply to a question. X1 is reply to question 1. So you will say yes or no. So x1 will be 0 or 1. For ith question, probability that x will be 1 is AI, very specific to the question. All probability is different. Answers are completely independent. And how many different outcomes can I have? How many different opinions can I expect in a questionnaire, in filling this questionnaire? Well, 2Q. That many possible different opinions exist. Now, suppose n number of people who responded to this is lambda times n. Lambda is 10. Per opinion, I ask 10 persons. And then I look what they came with their opinions. Well, this process is fragmentation of probability. Suppose this A1 is interval is the probability of answering yes on the first question. What is the probability that I will say yes and then yes? It is that I will take A1 and then I will take A2 fraction of this A1 because the length of this is A1 times A2. And what is the probability that will say no, no? Because this is probability that will say no, or 0. And this is probability that will say no. And then therefore the length of this is 1 minus A1 times 1 minus A2, which is probability of 0, 0. And if I continue, I will end up with lines like this, with the pictures like this. And then I'm saying A arbitrary. A spread in any way you wish. Then can we obtain some law here? Is there anything to discover mathematically, or it is complete chaos? Absolutely not chaos. We can say many things here. And first of all, we will say that the number of different opinions in our sample will not be of order of possible opinions. We will look in any such questioning as a mob. So we are all saying the same thing. We are expressing much less variety of opinions than possible. But we are not mob, but this is simply nature of this questioning. And if I take number of opinions or questionnaires which are filled, which I see k times and divide by the total number of different opinions which I see in my questionnaire, there will be a limit. And this is the limit. Well, I'm saying this easily. It's not very easy to prove, but, well, this is the result. And this is not Zipf's law. It's called Caroline-Rouault law. Rouault discovered in some other macro chain applications and so on, but we discovered it here. Okay. So these fractions became very stable. Maybe I show you just only this and then I will stop. Suppose Q is 10. So I ask you indeed 10 questions. And the total number of possible opinions is 2 to 10, which is slightly over 1,000. Suppose lambda is 10. So I ask 10 times more people. That's I ask 10,000 people. And it's 10,000. Now ask yourselves how many different opinions you should expect if that many different opinions are possible. Would you expect something like 900, 800? Just ask yourselves. I don't need the answers. But the answer is much smaller. It will be all small of 1,000. It will be something 200, 300. What is the behavior of each probability of each opinion? Now, of course, it will go to 0. If it goes to 0, this is, if I say that it goes to 0, this is trivial. But this is not trivial now, what I try to say now. If I look on average or expected number of opinion X, what will happen to this expected number? This Px is small, but N is huge. And I multiply these two, what is the result? The result is that for each X, this quantity goes to 0. These are only few which survive and somehow show my opinion pool. Yeah? And we know how quickly they go to 0. Well, this is the last quantity I say. I will forget about this, but I will say about this. What is this G and K? This was interesting quantity. Appeared during the Second World War in intelligence. They looked on overall sum of probabilities, which I see in my sample K times. For example, K is K0, then this is overall sum of probabilities, which I do not see at all in my sample. What is overall probability of such events? What can I say about this one? Well, forget about this, but what can I say about this? I can say something. I can say that expected value of this is quite small. It is expected value of total number of different opinions, different opinions divided by number of observations, and this fraction is small. Now, this fraction is small, however, this is what Laplace said in the same analogous question. He thought that this is 1 over n plus mu n. That was his reply. much more pessimistic than actually it is. The number, total probability of events which I do not see is small, but then we know how small it is of this order. I think we can continue this, but let me stop. Thank you very much for your attention.
Thank you very much. We have time for one question, maybe from the audience, and one from online audience. Yes.
So let me see if I understand the question, the problem with the wall, and the person trying to understand where the angle is correctly. You know, you had this issue where there was a random angle, and
Yes.
there was someone standing behind the wall.
Yes.
Okay, so am I understanding it right that the person standing behind the wall is taking the average of the y coordinates?
Yes.
Not the average of the angles. He's taking.
Oh, no. Or white corner. He doesn't see angles. He doesn't see the person and the source of light.
Yes, but he does have a zero, so he is able to measure y.
Yes.
But he's not able to measure the angle because he doesn't know how far away.
Yes.
I see. And you're saying that the average of those y's can be I mean, it behaves erratically.
It behaves the same way as one observation.
One y. Yeah, that's very interesting. Yeah.
Yeah.
Thank you very much. There is a question from online audience.
Do we have online audience?
Yes.
Oh.
We have online audience as well. Yes. Hi, I ask, why does the treatment of events as statistical ensembles lead to discovery? Does it lead to convergence?
No, it can very well lead to nothing. And it will then look very unjustified, very silly, very naive, and not interesting at all. But in these cases, which I mentioned, it happens so that the counting words in literature work leads to the statement that the relative frequency, so the number of events seen k times divided by total number of vocabulary, strangely converges indeed to quantity, and this quantity has clear mathematical expression. It's Zipf's law. And this is very unusual why this should be happening, but it does. And in Chinese emperors, it's similar thing, I think. Suddenly we see that the ensemble of statistical data is not whatever. It's not just who knows what, and any emperor rules in any way it wishes, and what happened. No, suddenly their life changes. You are young emperor, and then you rule for some number of years, and the old emperor look for some number of years. Should it not be in second case shorter than in the first? And then we discover that it's not true. It is discovered by naive statistical ensemble of such a magnitude of a data. And I think it is interesting because it's not very easy to explain.
Thank you very much once again.
Thank you.